Hello, welcome back. Now we are on energy level diagram and energy profile diagram. Let's start off with the first one, energy level diagram. This one just places reactants and products on the same graph to tell us what's the relative energy between them. They don't have a value here, usually we don't, but if we were to put one, for example, we put 500 and 300 for example. Because we know the energy along the y-axis, as it increases up, energy, y-axis values increases. So we can see that in the case of exothermic reactions, products only have 300, for example, and reactants have 500 kJ per mole, kilojoules per mole, right? This is the units in this chapter. So basically this is saying that for exothermic reactions, reactants have more energy than its products. On the other hand, endothermic, it says that products have more energy because it's higher up on the y-axis than reactants. So it's just the opposite. Basically, this is not tested as much, because you can see that even from the learning objective itself, it's talking more about energy profile diagram instead. So we will move on to that now. So this is how an energy profile diagram looks like. This is the case for exothermic, this is the case for endothermic. Let's start with the exothermic first. Basically, we know that in exothermic reactions, reactants have more energy than products. Let's go back to here. We talk about this here. Reactants have more energy than product, for exothermic. And the opposite is true for endothermic. So how we usually start off with the diagram is, we draw, this line first, reactants and products. The difference between them doesn't really matter because we don't have a value here. It's just their relative positions. As long as reactants, is higher than products, it's okay already. After we draw these two lines, we draw this curve here. This to denote, the reaction happening. Let me explain why. EA is called the activation energy. You may ask, why is it EA instead of AE if it's activation energy? Because, let me just write finish first. Activation energy. So from the word, actually it should be AE, right? But it's not because this is a subscript A. This E stands for energy, this subscript A stands for activation. So it's a subscript A and not EA on the same line. It's a subscript. So EA stands for activation energy. Basically, a reaction, doesn't just happen from a reactor, then it goes down like this to the product. No, it goes through this thing, this hurdle called EA, before it can actually go to the product. So this is like climbing a mountain, right? You have to, when you walk along the straight line to it, the mountain, and then you have to climb the mountain to its peak, and then you have to go down to get to your final destination. So this is exactly the same thing in the exothermic graph. Change in H is what we have learned before, right? Change in H, we know the formula, equals to bonds broken, energy of bonds broken minus bonds formed. The value, for example, maybe it's positive 200 kJ per mole. For example, and it will be filled here. This is where we put the numbers in here. So this is the two components in the graph, EA and change in H, which is the enthalpy change of reaction. So now we want to talk about the other one, which is endothermic. Similarly, we have the same graph, but endothermic, we know that the products have more energy than reactant. So we draw the products higher than the reactant. But we cannot draw the products on the left-hand side because products happen after reactants go through reaction, right? So products, although they are higher, they have to be on the right-hand side, whereas reactants have to be on the left-hand side. So it's the same thing. Now to get from my reactants to my product, I have to climb a hill. And this whole thing constitutes my activation energy, EA, and the difference between them is change in H. The difference between products and reactants are always the change in H. You can see from here, this is the difference, right? When I extend a line here, I extend a line out, this is the change in H. Whereas for this one, if I extend the line like this, and I extend the line like so, this is a change in H, because it's just the difference between products and reactants. EA is a bit different. EA, you always start from the reactants line. For example, this one. If I draw it in blue, maybe it's clearer. If I draw in blue, you can see that I have to start from this curve no matter what. And I have to start from this curve no matter what. So it's really, I start from reactant, and it goes up and touches the front of the product. Touches this area here. And this is how I should draw my curve. and it's really always starting from the reactant side, ending with the product side. Okay, and I'll get two different looking curves. This is exothermic, this is endothermic. Okay, so if you use the analogy of climbing a mountain, I think it's easier to memorize. Okay, now we'll talk about something a bit special. This is exactly the same thing as previously, okay, reactants going to products. Okay, I skipped the EA and change in H for simplicity's sake. But now it's something special because it's this thing called a catalyst. Okay, a catalyst speeds up reaction by providing alternative pathway. What do I mean? Remember, I have to climb this mountain, okay, from reactant to product, the white line, okay. I have to climb all the way up here and then going down to my product. That will take very long, right? For example, it will take maybe, say, 1 hour for this reaction to complete. But if I were to provide it with an alternative pathway with a catalyst, okay, you don't have to know the working principles behind the catalyst for now. You just have to know that it provides an alternative pathway. So now my reactants can go via this white line and can go via this orange line. So which one do you think they will choose? Okay, they'll obviously choose the orange line because it's lower resistance. Okay, they always want to go for the easy way out. Okay, and that's why they'll take this orange route instead, going to the products at a lower energy. So you can see, because we know that EA, okay, it's this one, right? For let's take exothermic reaction, okay, for an example, we know that EA is this much, correct? Usually. But now if I were to, so maybe let's give a value. So from here to here, maybe it's around 500. Okay, makes sense, right? This one is possible, 500 energy, worth of energy. But if I were to travel by this orange route, okay, imagine this is the center, okay, maybe I should draw the center. Okay, if I would travel by the orange route instead, this one only takes me, okay, here to here, only takes me 300 worth of energy, 300 units of energy. So obviously I'll take the lesser one, and that's what catalyst does. It provides an alternative pathway such that my reactant can go via a shorter hump, okay, and reach my products faster. Okay, similarly for here, endothermic, reactants can either go by the white line or go by the orange line. But we'll go by the orange line because it's faster. The energy required, okay, from the usual of this white line here, okay, usually it has to go by this amount of energy. But now I can ask it to go via this amount of energy. Okay, so obviously you will choose the lesser one now, and that is the orange one. Okay, and that's the idea of catalyst. It lowers the energy barrier, I mean, for the reaction to proceed much faster. Okay, and with that we are done with energy level diagram and energy profile diagram. So in this portion, you really just have to know to draw the exothermic and endothermic graphs with the correct labeling of axis and the correct components such as EA and change in H, for example. Okay, and that will be all for this sub portion.